Okay, so at the last lecture I was talking about corrosion resistant alloys and why you might want to use them and the problems that you have with joining them. And I mentioned quite a lot of the time cost. And you really need to think seriously about corrosion resistant alloys because of that cost. So if we took the plain carbon steel at X65, this is a table of relative cost that I took from a report a few years ago. So you can see that if you start to add alloying elements in the form of a pipe, or if you add a liner, the cost goes up, and the amount the cost goes up depends on what solution you choose. So X65 carbon steel is taken as 1. If we went for a 13% chrome super martensitic steel, which is equivalent to X80 in performance, that price goes up by a factor of 4. If you go for a duplex steel with similar properties to X65, it goes up by a factor of 6. If you went for a super duplex, which is the X80 equivalent, it's a factor of 10. So if the material cost is going up by 10 times, you've really got to need to use that. So we don't if we can avoid it. Liner materials are cheaper. So X65 lined with a thinner sheet of 316 stainless, that's an austenitic stainless, 2 to 3 times increase in cost. That's a much more tractable cost. If it was internally clad, if we had to spray material inside, then it's a bit more expensive. And again, that's the sort of thing that happens in pumps and valves, but not usually in pipelines overall. If we take a nickel alloy and line it, it's more expensive than stainless steel, and it's getting up to the cost of super duplex. And by the time you actually have an internal cladding, then we're almost up to the full cost of the super duplex at X80. So you really want to have to do that before you choose it. It's just too expensive for a large pipe run to do it. But for specific components where you might have a problem, it's the sort of things that people will consider. The duplex steels though have the advantage that if you can get away with an ordinary duplex steel, you can have large scale supplies, and you can have benefits in terms of weldability in those cases. Sometimes the clad steels are cheaper in the long run though, because although they're more difficult to join and maintain the corrosion resistance, they do have a cost advantage. So you can spend a bit more time working on the problems and spend the money in solving those problems rather than just buying the material. So for summary, for the materials development, for UOE pipe, which I'll talk about later on today, steel metallurgy and plate rolling techniques have improved so that we can now produce routinely good quality pipe at X80, and there are some X100 out in service as well, with excellent toughness, good weldability, and that's normal. So the last pipeline jobs that were commissioned in the UK for the main gas distribution network around the country, so we could move gas from the ports to where it was being used, those were all commissioned in X80. Previously, most of the pipes have been commissioned in X65, so we are moving to that grade. However, we don't have much use of anything more than X80. I know in Canada and in Japan there are small lengths of pipe with higher specifications, but this is more on the trial stage. Seamless pipe, quenched and tempered, gives you good high strength pipe for sour service, and you can get good supplies nowadays. The problem with the seamless pipe was always making sure that the pipe wall thickness was uniform, and that because of the way of manufacturing it has been improved, we've got better quality round pipes with good properties, and we'll talk a bit more about that when we talk about the pipe manufacturing route itself. High frequency welded pipe, not so much in the way of development, but certainly the grades up to 65 are pretty good. X65 are pretty good. It's usually used for smaller diameter, thinner wall pipes. A high frequency welded pipe is incredibly widely used in the water industry for the plumbing pipes for distribution of potable water. So copper pipes for the radiators that you can see there will be made by high frequency welding from a sheet. But it is used in some cases for gas and for oil. Spiral pipe, we've got hot rolled and water quenched strip with good strength up to X80, and we can make pipe with good toughness, and we don't have a seam that goes along the length of the pipe. We have a seam that goes on the spiral, which sometimes is useful for addressing that long running crack issue. So now good quality supplies are available, and it's really looking at how the suppliers have developed the quality control in their process, which dictates whether or not you might choose this. So again, there are materials that need to be developed, there are manufacturing processes that exist, and there is a quality issue is how well you do that manufacture. And when you take those all into consideration, everything's been improving over the past few years, and most of the suppliers that are well known in the industry do good supply. You know, so it's not a question that you're buying cheap steel with poor performance, but there are always problems. You cannot guarantee 100% performance from any material, so you have to manage those problems, and you have to manage the manufacturing process to get the quality issues down, and that's what's happened. So that was sort of the materials development summary. What I want to really talk about though today is pipe manufacture. So we've got good quality material in strip form, plate form, in billets. How do we turn that into a pipe? So I'm going to talk about submerged arc welded longitudinal weld pipe, helical pipe, again by submerged arc welding, seamless pipe, and high frequency welded pipe, either high frequency induction or electrical resistance welding. And these have different uses, largely due to the diameter which they're set up for. So seamless pipe, as you can see from this list here, tends to be used for smaller pipe diameters because it's more appropriate for that, whereas the submerged arc systems, UOE pipes and helical wound pipes, tend to be used above 400 millimeters diameter, and the high frequency welded systems for the really larger pipe systems. But there's a limit, so when you've got about 600 millimeters, the high frequency welded ones stop. So you've sort of got different size regimes. So if you know what the size of your pipe, the diameter is going to be, it sometimes chooses for you which process of pipe manufacturer you'll use. But if we've got pipes around 400 millimeters, nearly everything can be used. So we've got a process where we're going to take material from the steel plant produced by continuous casting, and then we're going to turn it into a product form that enables us to do different types of pipe. So this part of the process here, which we've talked about in primary steel manufacture and reheating, that's the same for all of the different product forms that we need to make pipe. But then we can split the pipe to go to a plate mill. That produces a relatively thick system, or a strip mill here, hot strip mill, which produces a coil, or it can go through a billet mill to produce a solid chunk of material, which can then be made into a seamless pipe. So up to this particular point here, whether you have a continuous casting or a batch casting method, you're just making steel. You then have to get that steel into the right form for whatever welding and joining process you need to make the pipe, or no joining process for a seamless pipe. So the initial stages are very similar in these cases, and we can take continuously cast steel and put it through any of these processes. And similarly, we can take batch steel, reheat it, and put it through any of these processes. So the steel company has quite a lot of flexibility in how they actually prepare the material for your particular process. Now, what I'm going to do is talk about how we turn steel into pipe. So I'm really going to focus on this part of the process rather than the basic steel making. So the most common pipe process, certainly for the pipes that we use in the UK, and has been around for a long time, is what we call the UOE process. And the U and O are indications of the shape that a sheet of metal is put to in order to make a pipe. So we take a basic sheet and we bend it into a U shape, and then we make a full cylinder, that's the O shape. And E stands for expansion. So once it's been welded, we then expand that to plastically deform it a little bit to make it rounder and to generally improve its properties, check that the welds are okay. So plate comes in from your steel supplier, which has been rolled to the right thickness, and has been hot rolled and cross rolled and then controlled rolled. So you've got plate which you've got with the right mechanical properties for the pipe. It then goes into an edge planing system where we try and make sure that the edges are absolutely perpendicular to the surface, so that we can line them up. If we make it into a tube, they've got to line up perfectly. The edges is then crimped, bent a little bit, and then we put into a U-press. So you can see the U-press that's going there. And then we put it into an O-press to make the O shape. Those are then checked and tack welded together. So they're welded in place so that when we put it through the full internal welding process, that the parts will line up properly. And then we have an internal welding process, and in some cases an external welding process to finish off the pipe. So we've taken a sheet and turned it into a cylinder and then welded it to make the pipe. So this is a sheet that you can see here. The edges have been planed and then they've been crimped up, and these runoff tabs have been added. So this is to allow the welding process to go beyond the end of the plate. So the starts and stops in the welding process are not included in the main part of the weld. This is because there's always defects associated with starts and stops of welding processes, and you want to minimise their effect on the longitudinal weld that you're subsequently going to make. And we're going to use submerged arc welding, which I'll explain a little bit later on, because that's the big welding process that's used for large engineering fabrications. It's suitable for very large parts. Okay, so we've gone through the plate, the edge planing and the edge crimping things. We're now going to talk about the Ewing process. So here is the tool, here, circular tool, flat sheet of steel, a very long press, 12 metres long or 18 metres long. So the tool comes down onto the surface and it presses and you get the U shape formed. So you can see the runoff tab that's there. So those two sides should be parallel now. So they started off flat and then you've shaped them so it's a U shape. And then you take that tool out, and there's a bit of spring back. So what happens is when you push it down, there is a recess here, which is the other part of the press. When you push it in so it makes this sort of shape, and then when you release it, it springs outwards a little bit because you get a little bit of elastic deformation as well as the plastic deformation. So this tool here is undersized compared to the internal diameter of the pipe, and you will allow it to spring open a little bit afterwards. And the stronger we make the pipe, the more that spring back, the more we have to change the size of the tool to get the right size. So you will see that there are tool sets here for different sizes of pipe, and tool sets for different grades of pipe as well. So your pipe mill will have a load of these things. So basically they bolt on to the support thing. So you'll just have a set of tools which you can match for whatever you've got. So pipe mills don't like to change the grades all the time. So if they're set up for X65, they prefer to run on X65 if they can. And if they then have an order which means change to X80, they'll set up for X80 and they prefer to run just X80. They won't be swapping from one size to another. So a pipe order is large enough that you can have dedicated tool sets for that particular type of steel.
The bottom is clamped at this current position?
You just lay this on this support, and you can see here there's a mating surface with the right curvature here. So the only clamping is from the load pushing this sheet down onto the table. You can see the rollers here where things have been lined up. So it's not physically clamped, but it's clamped by the fact that you've got to put a circular thing into a circular depression. So we've made the U shape, but that's only half a pipe. We need to make it into the full pipe. So this is the O press. So you're looking along the end here. So this is the U-shaped pipe, and the press has just started to actuate. So you can see the runoff tabs here. You're just pushing those surfaces inwards, and you can see the crimping then is necessary. Lifted that up to make sure that this fits inside the tool and will slide round to actually make the shape. So as we push these two halves of the press together, you can see that now we're getting a more circular shape. It's going to an O shape, and the edges have come right together at the top here. And the final press, when it's completely closed, this pipe should fit tightly all the way around inside the press. And we've got perfect registry here. So we've not got any overlap, or we've not got any angles and things like that. Of course, when you release that press, again, a bit of spring back, it'll open up a little bit again. But under load, it should have the perfect O shape in cross section.
So inside the press, is there any temperature?
No, this is cold. Cold. You've worked very hard to get thermomechanically control rolled steel with good properties. And if you heat it up, you'll get rid of all of that. So you do it cold. Okay. So because of the spring back, we tack weld just to hold it in place, so that when we do the main weld, we can make sure that everything's lined up properly. And we'll have some sort of clamping system around the outside to push things together to allow us to tack weld. So this is a tack welding taking place. You can see the welding process here. So there's a couple of welds, and then we've got a big clamp which is invisible behind all of the equipment there that's holding it all together. So you imagine you just pull the sides together, you clamp them, and then you weld at each end. You put the clamp in the middle. And then hopefully, if there's not too much distortion and residual stress, the whole weld from the runoff strips all the way through the longitudinal position, the metal parts are in contact, and you've got a good chance of one single submerged arc weld joining all the parts completely. So, tack welding done. Then we've got the submerged arc welding process to actually join it. And this is the bit that makes it gas tight. So here is a submerged arc welding cart, which is going along inside that tube. So that's why you can't do very small pipes by this method, because you can't fit physically the submerged arc welding system in it. So there's a picture here of a submerged arc welding process. So you have a wire, and you strike an electric arc between the wire and the parent metal plate. That's the pipe that you're trying to make. And that arc, which is a mixture of electrons and ions, the electrons travel and they heat up the parent metal, and the ions travel in the opposite direction and they heat up and melt the wire. And then the wire molten particles are ejected and then dropped to form the whirlpool. So under gravity in this case, because it's internal at the bottom of the system. So the world metal then is deposited, that's molten, and it solidifies here. Now if you did that in air, if you any welding process in air, the atmosphere will affect both the stability of the arc and also the surfaces that you create. The surfaces get hot because it's molten, because you've melted the material. It's at 1500 degrees C if it's steel. It will react with the air to form an oxide. And too much oxide in the whirlpool means very brittle weld, and you don't want that to happen. So what you do is protect that. And in the submerged arc welding process, we feed this granular flux onto the surface. So we have a big thick layer of granules of particle that when they get hot, they will give off gas that protects the surface, that doesn't allow that surface to oxidize. And they will also melt and become fused with any oxides that do form, and they'll form a solidified layer called a slag that's on the surface. Now, what tends to happen is, if you form an oxide in the weld pool, the oxide has a density of about 2, 3, 4, 5 grams per cc. The metal has a density of about 7 or 8 grams per cc, so the oxides will float onto the surface of the metal. And when the metal solidifies, they'll end up as this slag layer sitting on the surface. So the flux is chosen so that you have elements in there that can react to make these slags easier to form. So a protective flux might contain some carbonates, and when you heat carbonates up, they give off CO2, and that CO2 might be the protective gas. And then the calcium oxide can react with iron oxide to form a low melting point oxide that will float on the top and protect the whirlpool. But that's just one chemistry. There are many different chemistries for doing that. So the picture here shows what happens at the end. So the welding part is over here. This is the vacuum cleaner, which sucks up the unused flux, and then that's reused, so it's just transferred to the front of the system. And you can see here the weld on the bottom. See, it started in the runoff tab, and we're just going along in this direction. And the weld is sort of not the same colour as the metal because it's got this layer of slag on the surface, and you have to clean that layer off at the end of the process. And that's often done with something simple, mechanical, like a wire brush. So that's the U and O process, and now we've got the thing joined. The next stage is to actually weld on the outside. So we've welded on the inside the pipe, now we want to weld on the outside to make sure its complete thickness has been filled with weld metal. And then we do some testing to actually demonstrate that that pipe is going to be good before it's released. So again, this is that submerged arc welding process. It's a bit clearer here. These are feeds for the wires, and the wires are coming in, and this is where the welding is actually taking place. In fact, this is just a demonstration picture, so there's no welding, so there's nothing to see. So here is the flux being applied just ahead of those wires, and here is the vacuum cleaning up the excess flux at the end. So this one's got 4 wires for increased productivity. It's a larger system, so the outside welding tends to be done, with more wires than the internal system, just purely because there's more space that's available. And this then just proceeds along. You can see the weld has actually been made here, and it's just continuing along. This has been locally stopped for demonstrations, otherwise you might see something happening here, but with submerged arc welding it's not always obvious that it's actually running. And then Yep.
Would that typically be double V prep, or would it be a single V with a face on the inside?
In these particular cases, there isn't much preparation at all. Often it's a single V, and it happens naturally because as you bend it over, and when it relaxes a little bit, it relaxes into a single V. To be honest, different pipes, it depends on the thickness of the pipe. If you've got a very thin pipe, there's no preparation. As the pipe wall thickness goes up, then you go first single V and then double V. But that's different manufacturers will tell you different things about that. It depends on how much control they have over the owing process. There's always a little gap, you see, when they actually tack weld it, and you're actually welding into that gap. And as I say, because of the opening, it's a V-shaped gap. The outside weld they may not prepare. The inside weld they usually do. Okay, so now we've got, hopefully, a complete weld. Next step is to trim off those runoff tabs and then inspect the surface. There's a question mark. It depends how much you trust your process, whether you trim the runoff tabs off first or whether you inspect first and then trim off afterwards. So if you trust it, you trim. If you don't, you leave them on. So usually we do an automatic ultrasonic test to verify the quality of the weld, because we're then going to apply a mechanical stress to the system. And what we're doing is the E part of the process. We're mechanically expanding the pipe. And what this does is it plastically deforms the pipe, and it will relieve the residual stresses in the longitudinal weld, and it will ensure that the ovality of the weld ovality of the pipe due to the welding process is removed. So the expansion is a critical part. If you want to get pipes to match up perfectly, they have to go through this expansion process to be perfectly circular at the end of it. And it also enables you to fit into the hydro testing machine, so you pressurize it with water to make sure it will withstand the rated pressure. So each pipe segment that is produced is hydro tested, so that they can guarantee that the pipe will withstand the operating pressure and be therefore of the grade that is required. After you do that, you do another automatic ultrasonic test just to make sure you haven't produced any defects during hydro testing. So by the time that comes out, and you might do magnetic particle inspection, pipe end X-ray and radiography, or even final visual inspections, you should be able to guarantee as a steel supplier that each pipe segment that you deliver is fit for purpose. So the failure rates after these processes are very, very low. And they're usually for something that you didn't even consider during the manufacturing process. So you hope that you control it. So generally, if there's a failure of a pipeline, it's not a failure of the actual pipe segment itself, it's a failure of the welds between segments. And then you design the welding system so that the welds are less likely to fail than the pipe, and then hopefully the pipeline is safely designed overall. But you cannot guarantee that there will be no failure. All you can do is minimize the risk by going through these processes. So we'll talk a bit about inspection techniques later on, but this is an automated ultrasonic assessment. So you can see there's lots and lots of ultrasonic cells here. So these are often used by pulse echo or phase arrays. So you're making a sound pulse, picking it up here, and looking for changes due to defects and things. And by having those arrays at different angles, you can look at different levels in the weld. So you know exactly where the defect is and how big it is, hopefully, if you do this properly. Lots and lots of investment in doing this, but you have to guarantee every pipe segment going out, so that's what you do. We'll talk a bit about ultrasonics later on, but certainly for offshore pipes, automatic ultrasonic inspection of every pipe segment is required. Okay, what about expansion? Well, you've got this big internal clamp, and it's a mechanical process and it's cold, And what we're doing is we're just expanding that pipe. So we have a cam-driven system which has the segments, these outer segments that you can see here, which are just forced apart. And typically we expand to around 1 to 1.5% strain. So we're increasing the circumference of the pipe by 1.5%. And that will even out any residual stresses due to seam welding, and it will reduce what we call roof topping at the seam weld. When you weld, because the weld in an arc weld is not totally parallel, it has a V shape, then you get different amounts of thermal expansion at the top and at the bottom of the weld. You will tend to get distortion due to the different stresses that generates, and that will actually lead to a failure if you're not careful. And certainly it will make it difficult to match pipe segments up. You want them to be perfectly round, so the expansion process is good for doing this. So, a bit more testing. Hydro testing we have to do because we want to guarantee the pressure rating on the pipe. Other tests will be done depending on what the requirement is. So a second ultrasonic test, as I said, for looking at defects, and maybe even visual inspection. And the ends of the pipe will be inspected just to see that there is no handling defects, defects from putting the hydro testing flanges on, all of those sorts of things. So mostly for a UOE pipe, we have a 2-pass submerged arc weld, double submerged arc weld, DSAW, one inside, one outside. The wall thickness is really limited only by the forming capacity of the Ewing and Owing processes. We could weld much more thicker systems, but you need a very big press to actually press a 50mm pipe wall. You wouldn't do it. Most systems, 17-18mm is about the limit, and actually probably more like 10 to 12mm thickness is more the standard. Just depends on how much you're willing to invest in tons of press. Cold expansion to about 1.5% maximum strain ensures good dimensions, and that's the first proof test. Often if you badly welded the system and you miss something with the ultrasonics, when you try and expand it, the tube will burst. And then the hydro testing at 95% of the specified minimum yield stress for 15 seconds is your second pass-fail test. Okay, we don't go up to the specified minimum yield stress because there's a chance that you will cause some defects to grow in that process. And that has shown to be a reasonable level of proof test stress to actually guarantee the performance of the pipes from that process in service. So what about the defects that you get? Well, there are defects that come in from the welding process, and we get center and sidewall defects. So this is the internal weld and this is the external weld. This one was done first, and then this was done second. At least if I look at that, you might say actually the external one was done first and the internal one was done second, and that may be the issue in this case, but this is probably a special sample to make defects. So you've got a defect in here and you've got a crack in here. So these are center line and sidewall defects. So this probably is where this weld is a bit offset compared to this one. So you've not quite got enough heating of the material here. So this is the original edge of the material which hasn't actually fused with anything. And then that led to some more complex looking cracks. Sometimes you get a segregation down the middle of the pipe plate from the rolling process, and that can turn into a crack which then runs into the weld. You get those sorts of defects quite widely in submerged arc welding. So what we do is when we set up the processes, cut them up and have a look at them and see if a process that you're using creates such defects. Offsetting bad alignment, sort of things you have control of in manufacture are often the source of those sorts of defects. Lack of fill. Good weld, bad weld. I think any idiot could see that that's a bad weld. And visual inspection should tell you that you just haven't deposited enough weld metal, that the conditions for welding are wrong. This is almost like a solidification crack right down the middle of the weld, but you've got this big open hole in the top here. That's porosity. So this could be associated with gas escape. So you may deposit weld metal onto a wet surface and the water boils off, and that can create defects into the system. So porosity may be the cause of the defect, or it may be an effect of the defect. It's difficult to tell these cases here. That's why I say an associated defect, because what came first? Difficult to say. We talked about hydrogen cracking. So if you weld in very wet environments and you don't dry out all your consumables and things like that, if your flux was wet when it was applied, which might happen if your factory leaks and somebody leaves the door open, forklift truck going in and out all the time, then you can get hydrogen cracking. And you can see there's a lot of these chevron cracks near the center of the plate, and then there's some near the edges. So there was probably some segregation in the center of the plate, which made it slightly more susceptible to hydrogen cracking than around the edge. And you can see the hook cracks on the end here, just to show that it's hydrogen cracking. Not all defects come from the welding. Here is a case here where we have a defect at the toe of this weld, but that defect was a lamination in the plate originally. It wasn't actually something that was introduced during welding. And you can tell that because we've got this sort of scab of material being lifted up off the top here in a very large hole. And normally the stresses here are tensile that would stretch that downwards and would close those sorts of defects up. So that's a pre-existing defect in the plate rather than anything else. And this is the weld topping that I wanted to do, or peaking. So here is before the E process, before the expansion process, here is the wall of the pipe, and here is the longitudinal weld. It's a bit rusty, so this has been done quite some time ago. And here is a gauge which just measures the pipe diameter, and you can see it's a fairly good fit, except underneath the weld. The weld has sort of lifted the thing up. So it's no longer a totally round system, and the expansion would be necessary to actually make that totally circular in cross-section, and to relieve the residual stresses which have caused that topping process. And the other one here, this is the one that's impossible to see from most analysis unless you use your automated ultrasonic systems. You've got here the joint between the two pipes with no weld metal in it at all. So this is one submerged arc weld, this is the other one, and there's a bit in the middle that's not welded. And so that can be quite a serious failure. This is the sort of thing, if it happens, that causes a burst during the expansion process or during the hydro test. It's one of the big causes. And it usually means that somebody's set the power settings incorrectly in the submerged arc system, so that we get incomplete penetration.
The lack of penetration with MPA, can we find that out?
With magnetic particles, no. You'd have to use some sort of internal inspection system. With radiography, it's almost impossible to see because you get this line there. You might, if you were very lucky, get it lined up perfectly with the source and you would see it. With ultrasonics, you can bounce those ultrasonics off at different angles here, and if you had the right ultrasonic array, you could pick that up. But you've got to have the right array, and you've got to have the full penetration covered in that system. So in principle you can do it, but it doesn't always happen because people haven't got the complete coverage on their analysis systems. Spiral pipe is a little bit more complicated. Actually, spiral pipe is quite common. If you ever look at the inside of a toilet roll, the cardboard inner is a spirally wound tube. So making cardboard tubes for general use is done by a spiral manufacturer, and the processes are worked out very well for these small items with material that can be glued together. Doing it in steel is a little bit more complicated. So you can see the process here. You start off with a coil of steel, and you uncoil it and straighten it. So these rollers are driven at different speeds, so we can control the speed here and the speed here, and that means we can put tensile stress. We can stretch this material. We've got rollers here which can also plastically deform it, so we make it slightly thinner, so we cold roll it and give it good mechanical properties. And then we'll have some sort of inspection process, and you could cut out, if you like, bits of the strip that aren't very good and weld them back together. But hopefully you can ensure that the quality of the material is good enough that you don't have to do that. Then you have alignment rollers here. And then you have a set of complex rollers that turns this straight strip into a tube. And the diameter of the tube depends on the angle here that we have this line with respect to the tube. So by changing this angle here and knowing what the width of the strip we're actually using is, we can fix the diameter of the pipe. So you have to be able to rotate the welding part of the process with respect to the strip part of the process and control that very precisely. And then you have to have these rather complicated array of rollers so that we roll it up into the tube, and we match the surfaces here, which can be then joined by submerged arc welding. Again, the welding torch is inside here, and we're using these rollers to position things very precisely so that we make sure the torch is absolutely where it wants. So you have to control the pressure, you have to control the bite of the rollers, that's how much they grip the surface, you have to control the angles and the takeoff rates and everything else to get it out so that you match the speed of unrolling to the speed of welding that you're going to have. And then this whole thing is going along here, and then you can have some sort of heat treatment inspection stages and things like that further. And here it is happening in process. So this is the external weld being done here, and you could also have an internal weld being done at the same time, and the strip is coming in from the right and being rolled. You can see that weld is still hot, so it's being controlled quite well. It's an industrial process. It has quite a high degree of control, but it has quite a high degree of manual intervention to set it all up to go in the first place. So you might have 3 or 4 stations where you're making these helical pipes, and then you will have to deal with them. So you'll have some sort of accumulator here, you can see here, and you've got the welding processes taking place here and here, so internal and external welding, and you can have those all going through, and you might have multiple wires being fed, internal welding and external welding. You might have multiple stations of pipe, and you can make a certain length, so you'll be pushing, if you like, this pipe through from the strip feed, but you'll also have to have the ability to collect a certain amount of pipe in your manufacturing process. So the length over which you can do things will depend upon the setup in your factories and things. So, this might be your 12 or 18 meter accumulations or longer than that, and this might be the supply of the formed but not yet welded pipe coming in. So you can have multiple stations, and that's the way that economics is achieved in this business. So I would say that helical wound pipe was regarded as inferior to longitudinal wound pipe because it was difficult to set up. And there were many people in the gas industry who called it water pipe, and that was a term of disdain, shall we say. Because if water pipe leaks, it's not so serious, so it's a lower quality product. And the real problem was setting up the process, because it's much more complex. You've got to get your alignments much better. You've got all these rollers and things. You've got to integrate that with the welding processes. And you had poor dimensional control and roundness, and it wasn't so easy to achieve the same quality as with UOE pipe. Now the pictures I showed you were quite old. If you go to a modern helical pipe mill, there's a lot more computer control, there's a lot more sensors, and generally it looks much more of a high quality manufacturing process, and indeed the product that is now produced is much more high quality. And I think if you produce a good pipe mill, you can produce equivalent quality pipe by these processes. Why am I talking about this in so much detail is because if you're going for really, really big pipes, the diameters of more than a metre, then often you are limited to the helical pipes because you can't easily press those pipes by the UOE process. The loads are too high for very thick walls, certainly. And so once we see these very large diameter pipes, you then say, well, it's likely to be a helical pipe. Not essential, but it's likely. There are some special cases. If you've got to have, small runs for things like pig traps, and where you might want a large but short section of pipe, you can use what we call a 3-roll forming system, where you just take a sheet between a larger central roller and 2 smaller rollers, and if you roll them, rather like pulling a sheet of paper off the edge of your table, you get stresses set up and it will just naturally curve. So this is the engineering version of that, and you can make yourself a circular system. So for short lengths, you can actually make pipes. For very heavy wall pipe, it might be the only way you've got for doing it. So if you want something more than 28 millimetres, which is quite rare used, you might want to do that. For short runs, as I say, for pig traps and things, you might want to do that. And also, if you want to have a pipe which you're then going to bend in an induction bending system, you might want a heavy wall pipe made by this process, so that by the time you bent it, the thin wall is maintained and you've still got good mechanical properties. We'll talk a bit about induction bending later in the course. So this is kind of a special, but it's a very similar in size and dimensions to some of the things you can get from the spiral wound pipe systems. So I think, given the time, I shall stop here for today. What I've told you about is the 2 major manufacturing methods for pipe that have been used historically. I'm going to talk a little bit about high frequency welding pipe processes and seamless pipe processes at the next lecture next week. Hopefully, Professor Gibson will talk about plastic pipes with you tomorrow. That's the plan.